Hello, fellow chemists. In this video, we're going to take a look at bond energy. This is labeled as a basic video because there's really no information that you need to know to be able to follow along with the topics that I'm going to discuss in this video. So let's get started. Bond energy and atomic energy. Uh, what makes atoms want to bond? Meaning, if you have two atoms floating by each other in the universe, why do they interact with each other at all? And the reason is because that when atoms interact with each other, they become more stable. When they bond with each other, they become more stable. And by more stable, we mean they are lower in energy. So the whole purpose of atoms bonding is so that they can lower their overall energy and exist in a more stable state or a more relaxed state. And the major way in which atoms can lower their energy is by filling their octet. And what that term means is that the valence shell for atoms, if they can get that valence shell can get 8 electrons in it, it makes that atom very stable or very low in energy. And that is the main reason why atoms bond with each other, to fill their octet. And by filling their octet or filling their valence shell, they gain very low energy and they become very stable. So let's take a look at this diagram that I have drawn here. On the y-axis, we have energy, and on the x-axis, we have distance. If you have two atoms, as I have drawn here, two hypothetical atoms, and they're relatively far apart from each other, they feel no force from each other, meaning the nucleus from this atom that's positively charged can't really pull the electrons from this atom closer to it, and vice versa. So they feel very little interaction with each other. So their overall energy just kind of approaches zero because they don't affect each other at all. But then, once those atoms get pulled towards each other, they reach this magical distance where their electron clouds just start to overlap a little bit. And when that happens, you can see the overall energy for these atoms goes way down. This is extremely stable because energy is very low here. So this is kind of the sweet spot for atoms getting near each other and bonding. And we'll take a look at why in a minute. But these are very stable atoms. Their electron clouds are just beginning to overlap and they are very low in energy. Now what happens if you then push those atoms even closer together? And that's kind of represented by this drawing here. Now the electron clouds are overlapped a whole bunch, and the nuclei of those atoms are actually starting to get very close to each other as well. Well, once you start to push atoms really close to each other, you can see their energy skyrockets. This is bad for the stability of atoms. These atoms are very unstable. And it's pretty easy to see why. The nuclei are positively charged, and once you start getting those two positively charged nucleuses near each other, they start to repel each other at an ever increasing rate. So these nuclei, now that they're very close to each other, the protons in those nuclei repel each other quite a bit. And that's why you can see the energy going up almost exponentially. So why is there this one spot where the electron clouds overlap just a little bit that causes these atoms to be very low in energy? Well, the short answer is when they overlap just a little bit like this, it allows each of the atoms to fill their octet, meaning valence electrons from each atom can kind of hop back and forth so that each atom has 8 electrons in its valence shell. So let's kind of see how that happens. So I'm going to kind of blow up these two atoms here into kind of like a larger picture. So we'll make each of them a little bit bigger. Kind of like this. Now, we still will have a nucleus for both atoms. And the nucleus, put them in the center. They're still kind of far apart from each other. They're not too close. And you can see that the valence shells are just beginning to overlap here. So there's a little bit of overlap in the valence shells. Now let's take a look. We'll pick an element to actually look at for this, and we're going to pick, say, fluorine. And so we'll pretend both of these are fluorine atoms. And neutral fluorine atoms have 9 protons and 9 electrons. So I'm just going to put a plus here for the nucleus. I don't care about, counting the exact number of protons. But for the electrons, there's 2 electrons in each fluorine's first shell. So I'm going to put those in here. And then there's 7 electrons for each fluorine in their valence shell, or their outer shell, which is represented by this green circle. So we'll go 1, 2, 3, 4, 5, 6. And the 7th one I'm going to put right in here. And then for the other fluorine atom, we'll go 1, 2, 3, 4, 5, 6. And this one's 7th one I'm going to put right in here too. Well, you can see that these 2 electrons are kind of overlapping with each other. And what they do is they actually count for both atoms. So now if I count how many valence electrons each fluorine has, it's 1, 2, 3, 4, 5, 6, 7, but this electron from the other fluorine is going to count as well, 8. Well, this fluorine now filled its octet. It's very stable, very low energy. If we take a look at the other fluorine, it has 1, 2, 3, 4, 5, 6, 7, but this electron from the other fluorine counts for it as well, so it has 8. So you can see when the fluorines overlap, their electron clouds overlap just a little bit, it allows some of the valence electrons to interact with each atom, and then those valence electrons are counted as belonging to both atoms, which would then fill those atoms' octet, which in turn causes the atoms to have very low energy and causes the atoms to be extremely stable. Now, when we're looking at a situation like this, we then want to talk about the bond that forms and how they determine, well, how long is that bond? They measure the bond length by looking at the center of one nucleus and then going over to the center of the next nucleus. So this distance between the 2 nuclei of these atoms is called the bond length. And based on which atoms are bonding with each other, this distance could be different. Usually they're in the realm of nanometers, but it might be 12 nanometers or 18 nanometers based on which atoms are bonding. Because remember, all atoms, lots of atoms are all different sizes with each other. Like fluorines are relatively small, but franciums are relatively large. So which 2 atoms are bonding is going to determine the overall bond length. All right. I hope you have a better understanding of why atoms bond, why it's important to fill an octet, and why there's this sweet spot for how close atoms want to get to each other to have low energies. That's it for this lesson. I hope you learned something. If you did, subscribe and like, and I'll see you in the next video.